And thanks, everybody. It's great to be here. The work I'm going to talk about today grew out of a visit in 2008 by the director of the National Renewable Energy Lab, Doyne Farmer, who came to Santa Fe Institute to ask us if we could help them think out of the box and what were they missing. And during the course of that visit and a workshop that happened subsequently that Dan was at, if I recall, it became clear to me that what the costliness and the correct path to dealing with climate change really depended on not what technologies cost now, but what technologies will cost 20 years from now. So that set me on a path of trying to understand, trying to produce reliable answers to that question. And so that's what this talk is about. Now, just to provide a little context, energy makes about 75% of emissions. So if we can make the green energy transition, we've made most of the transition we need to make to deal with climate change, or at least to stop increasing greenhouse gases in the atmosphere. And the punchline that I'm going to deliver is that we can, and I'll come back and discuss what can means, make green energy transition quickly and a profit. And I'll throw out a scenario, at least a possible scenario for doing that, discuss a little bit about the possible roadblocks to making that happen. Now, most of the story is in this plot that I'm showing here, which is giving the history of the evolution of the global energy landscape over the last 140 years. And so we see in the panel on the left, where we have dates on the x-axis and cost measured in standard units on the y-axis. We see the cost of various forms of making energy through time. For example, here's the cost of, the price. So these are prices, not costs. Prices of coal, prices of oil, coal-fired electricity. And so you see they're kind of bouncing around. And one of the striking things about this is while they wiggle, there's no overall trend. In fact, I remember at this meeting in 2009, where Dan saying, we were saying, well, solar energy prices are coming down. And Dan saying, well, how do you know that coal prices aren't going to do that too? And that actually ended up with a paper that James wrote on the cost of coal-fired electricity, showing that yes, it did actually come down for a while, but then it went back up, decomposing that and finding the causes. And the main cause is that ultimately coal-fired electricity is driven by the cost of coal, which, as you can see from here, and comes out in mathematical tests, is essentially flat over time. These behave very differently than these. So you see solar energy, wind, batteries, electrolyzers. And so those have been coming down quite systematically through time. And at present, we're in a peculiar state where we have many different sources of energy that are all competing around roughly the same cost. So you can see it's a very unusual point in the history of energy. This panel over here shows the deployment of energy through time. So you can see traditional biomass remaining roughly constant, coal becoming dominant, oil and gas rising through time, nuclear power rising and then flattening out. And then once again, solar energy, wind, batteries, electrolyzers, all shooting up at rates where they're being deployed at around 40% per year. So solar energy has been increasing in deployment at 40% per year for the last 30 years. It's been dropping in price at 10% per year for the last 30 years, which is something unique in terms of historical energy supply. So the question is, what are these going to do? Are they going to just flatten out and remain around the same price level of the other ones, or are they going to continue to drop? And so that's what this talk is about. And then putting that together to think about the whole green energy transition. And by the way, stop me at any point if you have questions. So I'm just going to make a few observations about technological change. So these are empirical observations, which is that, first of all, technologies improve at very different rates that are technology specific. These rates are highly persistent, and this only becomes clear if you look at granular data so you can really identify individual technologies. And there's an identification question we can come back and say more about if people are interested. But for now, let's assume there's a such thing as a technology that you can track the cost of through time. And I'm going to argue we can use this to make predictions in one of several ways. One is to just note the trend. So here we take from over a span of 20 years, the price changes in goods ranging from hospital services to television sets, all starting at some standardized 0 point. And we see that over those 20 years, hospital services went up by 225%. The quality adjusted price of televisions went down by 95%. So in other words, televisions dropped in price by a factor of 20 over those 20 years. Hospital services went up by a factor of 2.25. And so this illustrates the point about diversity. It also illustrates my point about persistence. Hospital services went up every year. Television sets dropped every year. So these changes were quite persistent through time. This illustrates the point about heterogeneity from a different point of view. So we take the price indices for US goods relevant for US manufacturing from 1958 to 2011, group them by type. And what you can see in this, we plot now, make a histogram of the average annual growth rates in percent for the price. And you can see that most things, like here, there's a bell-shaped middle that most things sit on, and most things are not too far away from just going along with the herd. The herd's moving at the inflation. But then there's some set of things, in this case, all computer electronics related things that are dropping in cost at a much higher rate, suggesting that the heterogeneity of rates of change is a highly skewed distribution with a heavy tail on the positive side. We've done some other work that's not yet published that reinforces this point of view and illustrates it's not just computers that do this, though they were one of the main things that do. So how do we take advantage of this? Well, we're going to make use of empirical laws for forecasting technological costs based on historical data. The most famous of these is Moore's law. So Moore in 1965 made a pronouncement that semiconductor devices increased in density on chips, and that density increased, it roughly became twice as great every 2 years. He later on adjusted the time scale a little bit, and I always mix up which way the adjustment went, but it's been a remarkably accurate prediction now over a 70-year span. There's another even older law due to Theodore Wright, who you see here, who is a very interesting figure. He is the brother of Sewell Wright, who's a famous evolutionary biologist, and Theodore Wright, who is considered one of the founders of political science. But he was the black sheep of the family who went off to World War I, became a flying ace, and went into the aviation business. And in 1936, he wrote his one academic paper just mentioning that the cost of producing a specific airplane from a specific factory drops by 20% every time the cumulative production of that airplane doubles. Just an empirical observation. And so this is an example of that, actually, that I think James prepared for me a long time ago. And since then, there have been 1,000 papers written about Wright's law, looking at all kinds of other technologies and demonstrating that they did this. And the law has also moved from being about a specific item from a specific factory to being about much broader items like solar photovoltaic cells rather than globally, rather than solar photovoltaic cells produced by a specific factory. And that's the sense in which I'm going to be using that here. Wright, by the way, went on to become the head of aircraft manufacture during World War II and used his own law to successfully forecast the cost of aircraft production during World War II. And I'll come back and say a little more about World War II later. So Wright's law looks like this. If you write it mathematically, it says that if X is the cumulative production, that the cost of a good or a cost of the technology drops as X to some power omega, where omega is technology specific. And omega would be a positive number here for improving, meaning the cost goes down. Now, here is an example with 4 different technologies: transistors, photovoltaics, hard disk drives, and ethanol, where we plot the total cumulative production on the x-axis and the average unit price in dollars on this axis. And notice the plots are in log-log scale so that a power law turns into a straight line on log-log scale. And this gives you some feeling for roughly how good this works. It's not perfect, and it varies in how well things stick to these curves, depending on the technology. That also seems to be technology specific, but the pattern's pretty clear. Now, you might ask, where does Wright's law come from? So I would say it's not clear, but the best explanation is due to James and me and Sid Redner and Jessica Tranchik. And so we made a model where we assume that engineers just throw darts at a dartboard. We built on a model actually by John Muth, who, if for those of you who are economists, is the original architect of rational expectations in economics. So, but he also did in those days non-rational things, like assuming that engineers just throw darts at a dartboard, and what engineers are capable of doing is picking out which dart throws are better than which, and going with the best solution they found. And so it turns out this gives you something like Wright's law. It also actually makes a prediction about how omega scales with the complexity of the design of the device. As the devices become more complex or less modular, then improvement becomes more difficult because you have to coordinate improvements across more pieces. But let me just say, I don't think we fully understand Wright's law. And Wright's law is certainly also, it's a proxy in that cumulative production is presumably just a proxy for level of effort. And but cumulative production is much easier to measure than level of effort. Now, we took this and actually several other laws like Moore's law and acquired a library of technologies, history of technological costs through time, and tested this and tested actually several other laws. We tested 7 candidate laws, and we did this by pretending to be in the past. That is, we pretended to be at a given time in the past. We forecast each future date from that point in the past as if we didn't know anything about the future. And we repeated that for all past dates. And we scored the methods based on their forecasting errors. And we made an assumption that the improvement process is the same for all technologies except for parameters. I'll say more about that in a minute. So that allowed us to test our forecasts. Now, the data set we tested on is shown here. And as you can see immediately, it's a bit of a motley data set. There were 50 different technologies, chemical processes shown in black here, computer hardware shown in red. Actually, that data we got from Gordon Moore himself. A few consumer goods like beer, energy-related data sets there, genomics. So we had several different data sets. The data was acquired by just basically grabbing every data set we could find where we had the cost versus time for a specific technology. And the data was put together by my postdoc, Baillie, together with the help of some high school students. Baillie, we wrote a paper actually testing this and testing these different laws. And we showed that basically Wright's law and Moore's law came in with roughly a tie in this data set. And we also did some things to try and understand how large the errors were, but for various reasons, we couldn't properly test this. Now, the side anecdote I can never resist telling is that, well, one of the things we showed was an equivalence between Moore's law and Wright's law, and that if costs are dropping exponentially in time and deployments increasing exponentially in time, it's easy to show that Wright's law will hold under those circumstances. And that was the case for these 50 technologies. This was originally pointed out by a fellow named Sahel, who wrote several books on technological change in the 80s, and who mysteriously disappeared. One day, Sahel just vanished and nobody knows what happened to him. And Baillie became obsessed with Sahel, corresponded with his brother, and then about 2 years later, he mysteriously disappeared. So I'm sorry, I just can't resist telling this. I was, hope Baillie's out there doing something good somewhere. Yeah, I'm not planning on mysterious. I'm not obsessed with this. But anyway, thanks to Baillie's work that we managed to put this data set together. Now, how did we model technological change? So we rewrote Wright's law, which Wright just said there's a deterministic law that people had historically fit using regressions. We instead turned it into a time series model. So we rewrote it as a geometric random walk with drift that depends on where the rate of the drift depends on cumulative production of the good. And so if Y now is the logarithm of the cost, so the difference between the amount that the cost drops in, say, a given year is proportional to some constant, omega, times the logarithm of the ratio of the cumulative production in year t plus 1 to year t, plus a noise term that has some scale s. So this expression has two free parameters, omega and s. And we assume that all technologies follow this process. We take the data and we fit omega and s from the data and on past data, and then we use that to predict future data. Now, the key thing that we did was to derive expressions for how accurate the forecasts are. That is, let's assume the world really does follow this process. And to make things even simpler, let's assume that this noise process is an ID normally distributed noise. I thought at the time that was going to be a heroic assumption because I assumed that this would be heavy-tailed and there would be structure breaks and so on. But at least for the data set that we applied it to our surprise, it fit amazingly well. And we were able to derive an expression for the normalized errors. That is, if this epsilon here is the absolute value of the squared error, and this k hat, excuse me, that should have been s in the previous slide. I don't have my slides consistent. So that's the same as big S there. Then the ratio of these scales like this, where A, the normalizing constant that determines what the error is, has a term that's proportional to tau, which is the forecasting horizon into the future. So because this is a diffusive process, then the squared error goes according to scales according to tau, and actually, yeah. And then there's another term that goes according to tau squared, which has to do with the estimation error, where m is the number of data points in the data set that you're fitting this to. Okay, so in other words, you take some data and you do your best job to fit the parameters, then the error you will find a basis expression where this is a student distribution with m-1 degrees of freedom. So you can just derive this by from assuming that the world follows this kind of process. And so this plot over here shows what happens. The green line is the t distribution. The black line is what happens if we just assume a simple geometric random walk. And the red line is what happened when we assumed a random walk with put a little bit of correlation in, positive correlation. So in other words, what we found is to make this work, we had to assume that the improvement rates are correlated from year to year. And if you have a good year, then you tend to be followed by another good year. And so this is the result of making 6,000 roughly forecasts for all horizons up to 20 years, and then taking all the data from 50 different technologies and 20 different horizons and a bunch of different forecasts and putting it all into one bin and looking and seeing whether it followed this law that we predicted a priori would hold. And I should say, if I don't, this is with Francois Lafond. Yeah, well, Farmer and Lafond, we actually showed this first for Moore's Law, and then there's a paper with a bunch of authors led by Francois that shows it for Wright's Law, because Wright's Law was a bit harder to do. So what we found is that we could not reject our null hypothesis, which surprised us.
Did you try withholding data and using the data sets to test by making predictions of the data?
That's exactly what we did. So we did this process here. So we pretended to be in the past using only the data we had up to that point in time. And we actually did things like systematically looked, if we only use the 5 most recent points, we always saw that you always want to use the most data you can. Processes are surprisingly stationary. And so, yes.
You're treating Moore's Law and Wright's Law in some sense sort of an equal-handed way. And there, yes, there's this equivalence between the two, but that's under those special circumstances.
Right.
Conceptually, they're very, very different.
Very, very different. Yeah.
One of them is really the learning by doing deal, and
yeah.
one of them is exogenous technical change and inexorable march of progress and so forth. And they would have very different predictions, at least in principle.
Yeah.
If the factory just takes a break because of a labor strike for
yeah.
2 years, one of them says you're marching along, and the other says you're just chilling out for a while.
Yeah, I totally agree. And so this has been debated in the literature of which works better. And so to try and resolve this question, Francois Lafond, Diana Greenwald, and I wrote a paper where Diana managed to acquire lots of data from World War II, which is a good natural experiment for this, because unlike these other technologies here that just are coming down smoothly over time and are being ramped up exponentially over time, in World War II, the US went from being the 18th largest military to producing 2/3 of the military equipment for both sides combined. So we got data on the costs of 500 different types of military equipment. The data was crude in other respects. We really only had start and end points. We did have the full time series for maybe 100 of them. And basically what we were able to show by, and let me say, the key thing there is that the deployment ramped up enormously and then it went back down, plunged after as the war was ending. So from that, we could see that 2 things. One is the causality flows from, there's a strong element of causality flowing from cumulative production to cost. That is, and there was also an overall trend. Everything came down during that period. And so in other words, there was an exponential trend, but we assume the same exponential trend for all of them. And there was also a very significant Wright's Law component.
So a role for both.
Yeah.
The learning by doing and the exogenous technology.
Right. So that suggests that the causality is there, and that's why in what I'm going to show you in a minute, we're going to use Wright's Law rather than Moore's Law. Now, there's some problems with that too that maybe I can come out and talk about it at the end.
Well, I thought you just said that both exogenous technical change and the learning by doing are part of the story. If you pull it all into Wright's Law, and this goes to the heart of the paper today, if you throw it all into Wright's Law, then then you get these miraculous things if you just continue to.
Well, I mean, you do even better if you have Moore's law. So, so it's even more miraculous in that case. And a key clarifying remark, in the study we did for World War II, we assumed the same exogenous trend for all 500 technologies. To make this work for individual technologies, you really have to assume very different trends for different technologies. And so the exogenous trend that we saw in World War II doesn't really seem to explain Moore's law here. I think Moore's law is really explained by the fact that lots of technologies happen to have exponentially increasing production and exponentially dropping costs. I think I can skip that slide. Well, actually, let me just emphasize again that different technologies improve at really different rates. Here's coal. Here's the price of coal in terms of watts of electricity you could generate with a lump of coal, and here's solar photovoltaics, and here's nuclear power. So technologies behave really differently. Now, we'll move now to talking about climate change. How long will it take for technologies to mitigate climate change? What's the right investment strategy? Which technologies should we support, and how much will it cost? So let me just show what happens when you apply the kind of things I just mentioned to 4 key technologies for dealing with climate change. So we have in the solar photovoltaics, we're plotting the logarithm of cost versus the logarithm of experience. Experience is just a shorthand for cumulative production. The same for wind and lithium batteries and P2X electrolyzers. P2X means power to something, so that you start with electricity, you make hydrogen, and you use hydrogen to make a fuel like ammonia or one of several other possible liquid fuels. And so the colored bars here show the 95% confidence intervals for our forecasts. The black dots show the historical values through time. And if you stare at this for a while, you can see that it works pretty well. That is, things tend to stay near the center of the band that we forecast, and they never actually stray outside of the 95% confidence interval. Maybe 1 point here. And you would expect them to do 1 time in 20. P2X electrolyzers, you can see our predictions are a lot cruder because the data is, we have less data and the data is noisy. Remember, there's 2 technology-specific parameters, one for the rate of improvement and one for the noisiness. So this is just to give you a flavor for how this might apply to energy. I also just want to remark that, now this isn't so surprising because over the last 15 years, people are very aware that solar energy has dropped and become competitive. But back in 2010, I actually made a forecast in Nature, and we predicted that its cost would fall below that of nuclear energy or coal. And just to illustrate that at the time, like in 2014, The Economist was still saying solar power is by far the most expensive way to reduce carbon emissions. So I was moderately successful in forecasting. In contrast, the integrated assessment models and the International Energy Agency have done an extremely bad job of forecasting both deployment and cost of renewable energy. They've consistently been pessimistic about it. Here's a plot where we've taken the data here, plotted it in semi-log scale. And so you see a rough, noisy exponential decline. And you see forecasts made in the past that all go out at slopes that are quite different from the historical slope. Here we made a histogram of about 3,000 different predictions by various integrated assessment models that were reported in 2014 for the cost, for the rate at which solar would drop between 2010 and 2020. And this is the histogram of the forecasts, including the most optimistic ones. this is what actually happened. And similarly, if you look at integrated assessment models, they typically put in what are called floor costs. They assume that there's some cost where that the technology can't go below. So in these models, they assume they'll follow Wright's law for a while, but then they'll hit these floors and flatten out. They do this because otherwise the models just want to pump everything into them, and the answers become unstable. And this just shows historical floor costs compared with historical costs, showing that it just punched right through the floor costs as they've been put up in my forecasts. This will punch through all of them. These models, by the way, also have deployment constraints. They put in constraints in the rate of deployment. And one of the problems with these forecasts is that the numbers depend, and in fact, the quality, the evaluation of the scenario depends strongly on these two things, which have been more or less arbitrary. We've never seen any evidence for floor costs, so we don't put them in to what we're doing. Now, so we're going to provide an alternative, just doing something very simple. We're going to forecast technological costs conditional on deployment. So we'll throw out some scenarios. We can debate whether they're plausible or not. And so we're going to make a few representative scenarios, and we're going to assume that sector by sector useful energy demand continues to grow as it has been growing historically at 2% per year. So that is, we assume that there aren't any dramatic changes in lifestyle or anything like that. We apply the methods I've just mentioned, and then we just add up the costs of the technologies needed to make the energy sector work. We assume in our fast transition scenario that the key technologies are solar photovoltaics, wind, batteries, and P2X fuels. And why are we picking these? Well, we're picking these in part because we think they're good horses to bet on, but also because they have extensive data. There are other things that might be, may prove to be very important, like just moving power around in transmission lines, which we don't put in there because we don't have good historical data for how the costs will drop through time. So we use Wright's law to extrapolate, well, we extrapolate existing deployment trends in this solution. I'll show you in a moment. We phase out fossil fuels over the next 25 years, and we rely heavily on power to X fuel for energy storage. So we assume that we actually make so much P2X fuels that we can run the entire global energy system for a month, even if there's no sunlight or no wind, which is pretty conservative. We also use P2X fuels for liquid fuels for heat, shipping, and air transport and usages like that. Now, in the fast transition, let me actually show you what we do in all three of the scenarios we investigated for these four key technologies. So we show here the historical data for the deployment now of solar energy. So the average, the annual generation in terawatt hours for each year. We put a dashed red line through it just to show the trend. And then this is our fast transition scenario. This is our slow transition scenario. And this is our business as usual scenario. So I'm putting this up here, hopefully to convince you that we're not doing something that's crazy. We're extrapolating an existing trend. And in fact, we're assuming we begin falling off of that existing trend right away as solar reaches maturity and starts to flatten out. But at this rate, it does, solar energy and wind, you can see here, become dominant after about 10 years and completely displace fossil fuels in about 20 years, 25 years. So this is the same thing for batteries, showing what we assume for batteries in these three scenarios, and P2X fuels, where we assume for P2X fuels that we do stay on the existing historical trend for another 2 decades, noting that this is a much less mature technology than the other ones, and noting that these were on these exponential deployment trends for the order of 40 years. And by the way, this is standard in technology literature to assume that you have S-curves, that is, technologies tend to grow exponentially for a long period, and then they flatten out when they reach saturation. So that's what we're doing here. You had a question?
What was the question? How the business as usual occurs?
Yeah, our original business as usual, we more or less flattened this out to make it a straight line, and the referees complained that that wasn't realistic. So we softened our business as usual scenario, but it didn't matter very much.
Normally, price projections would be part of the quantity projections.
Yeah, so we are assuming these are assumptions, and we're then going to predict prices. It's true that integrated assessment models try and predict both of those in tandem. I think that's one of their problems. They're doing something they can't really do. And if you were going to do it well, because these end up depending very sensitively on the assumptions that I mentioned before. So this shows the transition in the scenarios in more depth, the fast transition, slow transition, and no transition, tracking all of these different energy technologies here through time, which is shown down here for the three different scenarios. And we're doing it for useful energy, which is the energy you actually use, the amount of work that actually comes out. Final energy, which is, say, final energy would be how much gasoline you have to burn to run your car. Useful energy is how many joules of work do you actually get out of your car. And this shows the requirements for electricity generation and storage, and which is then showing that we are talking about ramping the grid up quite substantially by about a factor of 4 in order to make this happen. Now, these show the forecast for some of the key technologies. I should have mentioned that while you can use Wright's law for oil, coal, and gas, and actually, because for those technologies, the omega parameter is effectively 0. And so you just get a random walk. If you use Wright's law, random walk turns out to be too diffusive. That is, over spans of time longer than about 10 years, prices just scatter around too much. There's some mean reversion. So we add in, for fossil fuels, we add in some mean reversion. So we use what's called an autoregressive order 1 model for oil, coal, and gas. And so you can see the probabilistic nature of our forecasts. And maybe I didn't stress that enough, that the generalization we make of Wright's law isn't just making point forecasts. It's predicting the probability of outcomes at different cost levels at different points in time. And what we tested was that probabilistic prediction. So you can see this is I think these are the 1 standard deviation and the 2 standard deviation error bars in the forecast. You can see the uncertainty growing through time. And we're also comparing to forecasts that existing integrated assessment models are making about what the costs will be at points of time, just to illustrate that our predictions are still substantially different than those of the other models. And so this is kind of the punchline. We showing that if this is under the 3 scenarios, so let's see, fast transition, slow transition, no transition. These are the, you can see how the fossil fuel expenditures are going down through time as we displace fossil fuels and replace them by renewables in the fast transition. So you see, we get already by here, fossil fuel expenditures are becoming quite negligible. Here we see in snapshot, let's see.
Sorry, this is a graph of?
This is a graph of the median expenditures on energy in each of the years shown. So 2020 to 2070, and then looking at the non-fossil fuel expenditures versus fossil fuel expenditures. So the white is non-fossil fuel expenditures and the shaded is fossil fuel expenditures. Here we show the net present cost. So we assume a discount rate, and to put all the different years together for the investments, we bring all the costs back to the present by discounting them. And this is what happens if you use a 2% discount rate. And again, you see the fast transition, the slow transition, and the no transition, illustrating the uncertainty, but also showing that the fast transition is on average cheaper than either of the other two cases. This shows the mean cost as a function of the discount rate, illustrating that we don't need to argue about the discount rate. The amount we save changes, but the fast transition is the cheapest regardless. And finally, these are emissions for the fast transition as a function of time, and compared with the slow transition or no transition. So now, maybe I'll just make a remark about technology investment portfolios. We have a paper where we look at investing in technology as a generalized process. And one of the things we showed is that you can't use intuition from Finance 101. Markowitz portfolio theory doesn't work at all in this domain, because, you know, in Markowitz portfolio theory says that if you have a bunch of assets, and if you have a positive return on all the assets, and if they're not perfectly correlated, then you should diversify by scattering your bets across all the assets. But if all these assets are following Wright's law, you have something very different, because to make progress down the learning curve, you have to invest in them. And so if you really knew which one had the best characteristics, you should just pick that one and put all your money in that one. But if you have uncertainty, then you need to spread your resources across the assets. And so with a situation you're in, a typical technology investment case shows you don't want to put one egg in every basket. You don't want to put all your eggs in one basket. You want to decide, you want to put most of your eggs in a small number of baskets, depending on how much uncertainty you have in what the situation is. And it also shows that you get a lot of extreme sensitivity in these kind of portfolios. So now,
Is this a good time to ask about direct air capture?
sure.
Because in your previous slide, you didn't include that, and sort of
Right.
there's a family of a group of people who would say that actually instead of P2X, it would be direct air capture plus fossil fuels.
Yeah.
And that would be additional, so you put that in with an additional Wright's law thing. And
Yeah. Yeah. So
what happens? Of course, we don't have enough data to estimate anything at this point.
yeah, I mean, there is some historical data on direct air capture, and it doesn't look good. It hasn't come down.
Yeah.
The other thing is direct air capture depends on fossil fuels being competitive without direct air capture. We predict that we're going to reach a point where that's not going to happen. I mean, where that won't be true fairly soon. So if fossil fuels aren't competitive without direct air capture, they certainly are competitive with it. And you know, also direct air capture has all the kind of characteristics that make me think it's not going to come down very much. But that's more of a subjective judgment. Now, that's different from asking the question of, are we going to need to use direct air capture to just pull CO2 out of the air in the future? And that's another story. And, you know, here again, the low cost, what we're predicting helps that, because we're predicting electricity should become very cheap, particularly if you don't need to deal with storage. And so you know, you could easily imagine that that the cost of direct air capture is going to come down quite a bit using solar electricity. Now, of course, what I've been talking about so far relies on extrapolating technological trends. And, you know, one would like to go to something more fundamental in understanding this problem. So we've been thinking about, excuse me, different ways of doing that. For one thing, let me just say a little bit about Wright's law. You know, Wright's law is a crude approximation at best, because if you pick a given technology, say take solar photovoltaics, well, it's composed of different things. There is the cost of building the cell. There's a cost of putting up the frame that's going to hold it in place. There is the installation cost, the distribution cost, and these things all behave differently. So generally, you want to decompose things as much as you can and look at the scaling relationships separately. This actually relates to a paper, another paper of mine with James, that James is the lead author on, where James showed that if you take industries and you ask what is driving the price index of an industry, that most of the improvements in the price, 65% of the improvements on average in the price index of an industry come from price improvements in the inputs to that industry. So to really do this better, you want to think about the economy on a more fine-grained scale, and you want to think about the interaction of the different technologies with each other. So we've been working on trying to do that, making more disaggregated models, and maybe just lift the discussion up a little bit. We've been pursuing a method of sort of modeling climate economics in a distributed way with, on one hand, we have our energy systems model, which is the version I just described to you. We're like, for example, making this be regional instead of global, which already gives significant improvements in terms of providing better advice. Trying to extract information we have about technological change, for example, coming from analysis of the patent space, where we see interesting patterns. Like if you go back and look in the 50s, nuclear power was if you do a page rank for patents, nuclear power sits in the middle and fossil fuels sit in the middle. If you do that now, renewables sit in the middle and nuclear power and fossil fuels are out on the periphery. Excuse me, work on green industrial strategies, that is thinking about imports and exports, stuff that overlaps with the work Ricardo's group does. And thinking about production networks. So we have models both at the level of industries and of firms, going beyond traditional input-output models to make dynamic models, which we made use of during COVID as a sort of a side thing. We've been talking about hooking this up with agriculture and land use models, more sophisticated models of household. In fact, we have a model of occupational labor diffusion. And so we're doing work now where we're coupling together our forecast for what's going to happen to the production network when we rewire from fossil fuels to solar power and wind and batteries and electrolyzers. And then how does that play out in terms of occupational labor? And then thinking also about treaties and government and how that interacts with all of this. So we're basically pursuing independent projects in each of these panes, but also starting to think about how to paste them together, at least pairwise or triple-wise, to make improved forecasts and put in more fundamental information. I think this suggests that doing the things that we need to do to support this. Yep.
So I'm wondering what the cost of the raw materials to produce this kind of technologies.
What? Sorry.
The cost of the raw materials.
The cost of the raw materials. Yeah. Yeah. So, well, that's an interesting question in that when you go back and start looking at raw materials, like things
lithium, copper,
yeah,
other kind of
things you mine out of the ground, there's a quite striking, not well appreciated fact that actually James was the first person to introduce me to. James went and looked at the USGS data and observed that they have a century of data for more than 100 different minerals. And he fit some time series models to those. And what you see is once you adjust for inflation, they're all flat, except one exception, industrial diamonds. Now, industrial diamonds aren't something you mine out of the ground. They've dropped by a factor of 100. Everything else, nothing has changed by more than a factor of 10 in price over a century. Now, that suggests, so raw materials, if they're things you're mining out of the ground, my prediction is they aren't going to get much cheaper. What gets cheaper are the processes for, making them into things. And that's where the progress happens. I mean, the other thing you might have asked about is shortages of essential materials. My impression, yeah, there may be some shortages of essential materials, but when you go back through the history of technologies, shortages of essential materials, whenever there's a bottleneck due to an essential material, another material is found that provides a workaround. And there are quite a few historical examples of that, like chlorofluorocarbons for refrigeration and many others. So to wrap up, I think, what have we shown? Well, first of all, I think it's important. It's been clear for some time that renewables were getting cheaper and cheaper, but people were still viewing the renewable energy transition or the green energy transition, getting rid of greenhouse gases, as a burden. Who's going to take on that burden? We're saying, actually, no, it's going to be cheaper than going on the way we are now. So even if you're a climate denier, you should be willing to jump on board to make this happen. And it also, I think, reframes the whole discussion from having climate change be a burden to have it being an economic opportunity. And the players who get involved, the firms and the countries who get involved, are likely to acquire the expertise to be players in the economy of the future. And so I think it really reframes the whole discussion. Now, we also, as I said, we were just throwing out the scenarios as assumptions, not as something we're deriving from first principles, though we tried to make them plausible by extrapolating from existing trends. But stuff has to happen to stay on those trend lines. In particular, I think the biggest one is the grid. We need to expand the grid globally by a factor of 4. And that's a pretty big change. It's expensive, but if you look at paying, a grid, even let's say the grid cost was $500 billion per year. I think that's higher than the number we've settled on now. But because we're already paying $4 trillion a year for energy. So if we can reduce energy costs by, say, a factor of 2, then that dwarfs the cost of building out the grid. But we have to worry about the political roadblocks to building out grids and doing that stuff. My son works for the Federal Energy Regulation Commission, and he said that there's enough proposed renewable energy projects sitting in the pipeline, I mean, not approved yet, but having been given to the commission, that if they approve them all, we would more than double the electrical capacity of the US. They can't approve them all because there isn't grid capacity to put them all online. So we really have to deal with that. We did look at stranded asset issues, by the way, and we found that that's not so bad because, you replace a gas station every 25 years. We're turning over our infrastructure all the time. So all we have to do is let the old infrastructure expire and replace it with infrastructure for renewables. And we pretty much get there without stranding that many assets. We do need a push on storage technologies. We need to stay on that trend for 20 years if we're going to make it. And as I already said, we reframe climate change as an opportunity. And, I found myself, I was sailing along the North African coast this summer. So this is a photo I took from my boat of a coal being, and this would have been in Morocco. And dealing with the bizarre police states in Algeria that have to do with, you have a military government that controls the key resource, oil, and, keeps the whole country under an iron fist. I think there are going to be substantial geopolitical changes as a result of this transition. 20 years is pretty fast, and countries like this are going to have serious problems dealing with it. So, question, please.
Yeah,
So I have a question. I appreciate your comments about the grid. I would bicker with the numbers a little bit on scale, but similar scale. A Princeton study of a net zero economy said, yeah, 4x existing. So total would be 5x, but you would need 4 times you need to build additional transmission capacity that's 400% more. So it's a five-fold increase, whatever.
Yeah, that's what we're saying too.
That's the same number.
Yeah.
And of course, upkeeping that, I think it's important to remember though, that today in Massachusetts, and I suspect in Brooklyn, it's not that different. Generation is about 45% of our electricity bill. And distribution is about 55%. And if you look at the investments required for a renewable grid, that includes some storage and some or backup capacity or whatever you want to do.
Yeah.
Looks to me like it's going to be closer to 80-20, if not 90-10. That is, the cost of generation is going to be a more and more insignificant factor in the overall price of electricity. So that makes me wonder whether, just because solar and wind get super cheap, doesn't mean the price of electricity is going down. In fact, it could go the other way. In fact, when I talk to most electricity policy people, they think electricity in a renewable grid is going to get more expensive because of the massive transmission system and all of the distribution challenges of balancing it and maintaining it. And that, yes, it's sort of like the question of module cost versus balance of systems. Yeah. But learning curves are harder to see on the transmission and distribution side. And the same is true for hydrogen. Right now, the electrolyzers are about 20% of the cost of making hydrogen. Yeah. So.
Well, and the other cost?
Well, there are things like storage tanks and, and stuff where learning curves may happen, but not as obvious that giant storage tanks are gonna come down in cost dramatically. And that's not even including the distribution effects. Yeah. The other thing is people in these literature often confuse cost and price. So they compare the cost of making hydrogen with the price of natural gas, which is not the cost at the wellhead. Yeah. And so I just wonder what you think about that tension. Yeah. Well, so we agree that the grid's going to be expensive, and we assumed we spent a lot of time researching, what the literature says about what it costs to install new grid capacity. And there's of course a difference of whether you're talking about transmission or distribution. And there's a difference of whether you're putting more wires in an existing line or whether you have to build a new line. But we made pretty conservative assumptions. We assume there's no learning, that the costs remain the same as they are now. We just scale them up because we're doing a factor of 4 more. So we increased the cost by a factor of 4 or 5. And and what I think the people you're talking to don't realize is if the other cost comes down, then if you can get an upper bound by just asking, what if the generation were free, right? So 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 we tried to do that. Now, we're very open to seeing whether our numbers are, having people go over our numbers and see whether they're correct or not. So, but I agree, the devil's in those details. It's also true that it's very tricky. You see, when you get to fossil fuels, there's no meaningful statement about cost of fossil fuel production, because you have places like Saudi Arabia where it's, a few dollars a barrel, and shale oil in Canada where it's $50 a barrel. And so the price of fossil fuels depends on what the marginal cost is for whatever the marginal supplier is at that time. And that's why it's so volatile. That's why I think one of the big side benefits of renewables is that we're going to see much less volatile energy costs as a result, because there's no reason to believe we're going to have that kind of mechanism where we have such a radically different set of costs and you're moving up and down the marginal price point all the time based on fluctuations in supply and demand. That curve's going to be a lot flatter. But yeah,
sorry, I'm trying to remember. I'm feeling did I address all of the things you brought up?
Oh, I just talked about the fact that
Yeah.
electrolyzers are a pretty small percentage of the cost of hydrogen.
Yeah. Well, of course, you know, in that plot I showed with the different technologies, there were a bunch of black ones that were chemical processes. And one of the things you see is chemical processes all tend to behave about the same way. So it's one of the more understood classes of technologies. And there are big economies of scale from things like tank size, where you get surface volume surface volume relationships help. So I think electrolyzers will come. I mean, from looking at related technologies, I'll be very surprised if they don't come down in price as roughly we would expect from the history we have so far. But time will tell. Yep.
In a world where generation becomes like exponentially cheaper, but transmission costs maybe are the bottleneck and stay high, do you think that there's any world where this generation becomes like radically decentralized to the point where we don't need such intense transmission systems? Like any scenario?
Yeah. Well, I mean, that's another way to answer Dan's question, in that if, you know, solar energy becomes so cheap, you can just paint it on the roof of a building and then the building is collecting solar energy, then you have a lot of possibilities for decentralized generation. You still are going to need to deal with storage. Now, electric vehicles already are going to increasingly provide a form of an example of decentralized storage. And, you know, the costs we were looking at were costs for industrial installations. There's a shift for localized, decentralized generation. But if the costs come down enough, then that shift won't matter much anymore. So, yeah.
I would like to understand the connection between different technologies. Solar technology is related to the batteries and related to the iron production and so on. And you are trying to explain how different technologies are connected and just maybe one curve of reduction of cost, or
No.
Is independent in technology by density?
Yeah, you really have to go technology by technology. Now, there is a question of what is a technology. You know, there's 20 or 30 different flavors of solar photovoltaic cells right now. And it's not clear if all of those follow the same scaling. Many of them likely do, because they're somewhat similar processes. You know, the technology is always evolving through time, so the technology is always changing. So nonetheless, what the data suggests is you can sort of designate something as a technology and look at its cost through time. Now, coal-fired electricity is a good example where up until the 80s, people didn't care too much about sulfur emissions, and then people started caring about it. So you might think a joule of energy is a joule of energy, but there's dirty joules and clean joules. There's intermittent joules and steady joules. So there's dangerous joules and safe joules. So nuclear power suffered from that problem. So your designation of the technology can shift and the cost can shift if the requirements you're placing on it change, as they did, say, with coal and nuclear power. But this goes back to what I was alluding to with this plot I showed back here, for our attempt to try and take a more holistic view of the economy and use that to think about climate economics, because we would like to be able to track all the technologies comprehensively and think about the ecology of interacting technologies and use that as the framework in which we think about things, rather than using what might be an inappropriate level of aggregation and that puts noise on what's happening. Because you expect things like distribution to scale very differently than technology parts. So we're increasingly moving towards trying to find the right levels of decomposition and then combine things, often splitting things into their inputs. In the paper, James wrote a paper on coal in, I don't know, when was it, 2013 or 14, back there somewhere. And what? 2011, okay. Where, you know, we decompose coal-fired electricity into operating and maintenance, the cost of mining the coal, and the cost of building the plant. And we saw that those three things really behave differently. And it was very useful to split that apart. So it's a tricky question that requires a lot of case-by-case judgment. Yeah.
Hi, Kate Manager from the Growth Lab. A lot of the investment in these technologies has been, you know, public investment that's variable over time. And have you found that that investment makes a difference as the rate of change of technology? Or...
Yeah. So it's a bit hard to say in a rigorous way. It certainly seemed like there's in Germany, there was massive subsidies for solar energy that did correspond to a significant drop in price. So this is usually called feed-in tariffs. And you know, when you think about, let me actually go back all the way back to the beginning. Oh, wait, no, I'm going the wrong way. If you think about these curves I'm showing here, okay. You know, how does solar solar is very expensive back at this point in time. And its cost keeps dropping. Well, the very first solar cell was in 1958, the Vanguard satellite. So one example, it had a cost that put a point on this curve over here that we're not even showing. Then people started using it for, you know, weather stations at the South Pole, places where cost wasn't a big issue. And then it got more and more niche uses. So the essential thing for a technology to roll out like this is that there be a set of niches such that it can keep advancing along. And as it does, its costs can drop. And so it's important to keep that going. And I think the cost supports, the price supports were important in keeping that happening. But I haven't seen a good study that really teases that out and shows cause and effect, and it's probably pretty hard to do.
I guess there's price supports for deployment, but also there's public investment in innovation. Which,
Yeah.
You know, if innovation is
Well, and you know, that's critical. And you know, there's Mariana Mazzucato, but others have done studies too, showing that public investment in technology has played a major role in seeding these things. Yeah.
So if you look at first principles modeling of solar PV manufacturing, what you find is that the costs have come down so much that you're essentially paying for the material and the input energy to make the solar cell. So like the prices have come down to that level. And I'm curious, like when you're applying Wright's law, when you using historical data, if you keep expecting that price to go down, are you saying that, so is your definition of solar then broader than just the current paradigm, which is the silicon paradigm, or are you thinking that we're going to evolve into new?
I think we will evolve into new technologies. We're agnostic about that. What's predictable is the future costs. What is not predictable are the solutions that deliver those costs. I once heard a fascinating talk by a guy who was a chip designer. This was at a meeting at SFI maybe 15 years ago, and they were talking about Moore's Law. He said, "You guys all assume Moore's Law is just inexorable. And he said, having been a chip designer, that wasn't the way it felt to us at all. We felt like we were looking at a brick wall. We couldn't see any way to get to the next step. And then somebody would come up with an idea and and we would break through and find a solution. And miraculously, that happened over and over again. And Moore's Law has sustained through that whole period. You know, some people say Moore's Law is just a self-fulfilling prophecy. That's clearly not true, because for one thing, when Moore wrote the law down, nobody else was aware of it. And it is true that it has been useful for people to plan, right? And I mean, a great example of this is my friend, Alvy Ray Smith, who is the inventor of CGI graphic techniques for Pixar. And he said they basically had it all ready to go 5 years before it actually got rolled out. And they knew they just had to wait for Moore's Law. They had all the techniques down And they waited 5 years, and sure enough, then Toy Story was the result. So it does allow you to plan, but it's not like it's a done deal or that it makes itself happen.
So just to clarify, so even though the omega parameters so far for the PV technology is predicted using silicon data, you're saying to keep it going, the prediction can come from any changing paradigm.
You see this if you look at, say, information technologies, where we made a transition from mechanical information devices to vacuum tubes to discrete transistors to integrated circuits. So each of them has its own curve, but the envelope that they followed is quite smooth, despite the fact that you're leaping from technology to technology. Let me, yeah.
So why do you think nuclear electricity hasn't acted a great in Moore's law? Because this also involves a technological factor, right? So I would expect it to.
Yeah, so it's a mystery. I don't think we have a good understanding. Now, people have speculated that certain properties like modularity matter. Actually, our theory with James has something like modularity that we call design complexity. And if you go out and test that, you do see that, and there have been a couple of tests from our theory, that indeed, as the design complexity goes up, the learning rates tend to get worse. But it's very noisy, very noisy. And it's like one of the facts that I think is amazingly strong is this one about stuff you mine out of the ground. But if you look at the way you extract oil now, it's incredibly sophisticated compared to what was done a century ago. Now, there's been a trade-off between the oil gets harder to find because we pulled so much out, the technology gets better to find it, but it seems very surprising that for 100 different minerals, you discover that those two trade-offs are just balancing each other across the century. You'd expect U-shaped curves that it would drop and then it would go back up. And that's not what you see. So there's something else going on there. Nuclear reactors are, well, a couple of things. If you read an account of what they have to do to clean up a spill in a nuclear reactor, it's pretty complicated. And so they're complicated pieces of technology. The French have maybe had a little bit of success in standardizing it, so to make it cookie cutter, but it hasn't really paid off. French nuclear power is very expensive too. There's a school of people very strongly advocating for making modular nuclear reactors, small nuclear reactors, not going to fly. I mean, because they're fighting a big scaling law to begin with. There's a reason why they made them big to start with, and you have to make that back up, and there's just no way they're going to do that. But there's a mystery. There's still a mystery. There's no way to predict a priori which technologies are going to improve quickly and which aren't. It's a big problem, a fascinating problem. Yep. Oh, sorry. He hadn't had a chance yet.
Yeah, so my question is, given the recent Wright's law, it seems it's only a counter advantage. So it might be that the right strategy is I wait others to drive the host down and then I come into this field.
Yeah.
Do you see a chance of early mover advantage into this field?
Yeah. I see your argument now, and there's certainly an element of truth there. At the same time, if you look at, say, the Danish experience with windmills, the Danes were early adopters of windmills and acquired expertise in windmills, and then they ended up becoming designers of windmills and have an industry around windmills as a result of that. This goes back to what Ricardo always stresses about know-how. So you get the know-how by being there early on. And if the technology has a sequence of niches that allow you to move up this curve, you start with a small business and you grow it through time. And so that's the flip side of the argument or the concern that you raised.
And is this increasing of false trends similarly across countries?
Well, so we did a study of geographical variation in solar and wind prices. And a couple of things strike you. First of all, you might think that countries that have good solar and wind resources would be the one to install the most. It's roughly uncorrelated. It really has to do with politics. And there is a significant geographical variation due to things like how often the sun shines and institutional factors about installation costs in country A versus country B. But roughly speaking, if you look at solar energy, in the course of a decade, at a 10% per year improvement rate, you move from the 95th percentile to the 5th percentile in the course of a decade. In other words, if you're the place that had the most expensive energy in the 95th percentile, then by a decade later, you'll have the same energy costs that the people that were in the 5th percentile had. So that roughly gives a scale of the geographic variation versus the temporal variation. That said, we are trying to build out a regionalized version of our model to deal with that kind of thing. Ricardo?
Let me ask you, you just mentioned the cost, who's installing photovoltaics?
Yeah.
And you said it was uncorrelated with insolation rates but the sun shines for free.
Yeah.
And the wind blows for free. So in these technologies, essentially, all of the cost is the fixed cost of installing the stuff with very little variable cost.
Right.
So when you work out the cost, whatever the equipment is, and let's assume that that's perfectly tradable and it has the same price everywhere in the world. But the other important component of the cost is the interest rate.
The interest, yep.
Yeah, and interest rates vary dramatically in countries.
Yeah.
By country risk factors and things like that. So that in the we've seen many PPAs, power purchase agreements at $20 a megawatt hour of solar. At the interest rates that the market demands in the Dominican Republic, you cannot get it below $70 a megawatt hour. So that would explain why, even though the sun shines more brightly in the Dominican Republic than it does in Germany, it's more efficient in Germany after. So
it could be that we didn't look at interest rate correlated, and so that might be. But that's driving a lot.
Interest rates are going to be an issue in the deployment, and some people thinking about how can you make the finance, the cost of finance, or say something in Namibia, not be related to the current yield on their government bonds, because at those yields, nothing.
Yeah. Well, one of the interesting things that people didn't anticipate that's boosted solar rollout has been that people have been willing to offer very low interest rates for solar projects, just because in contrast, say, to nuclear power projects, they've been very reliable in terms of if the project gets going, it tends to be delivered. The uncertainties are much smaller than in other domains. So solar has benefited. Certainly it's benefited from the fact that we've had low interest rates now for 2 decades. But it has, among energy, it gets low interest rates because it's reliable.
And there won't be any stranded assets.
Yeah.
But
Yeah.
Another question. You're going to quintuple transmission capacity. You're going to have, batteries galore going everywhere. Do we know what's the size of the mining boom that will be required to accompany that transition? And eventually I can imagine that in the long run, the circular use of these things might reduce the things, but how do we know from where we are? What's the mining boom required to get from here to there?
Well, it's substantial. It's substantial. And, I haven't looked into that in as much detail as I would like, but the studies I've seen don't suggest that it's, and they suggest it's doable. And that the, you know, there was a review article in PNAS 6-8 years ago comparing the environmental impact of different technologies, and solar, even when you take into account the need for rare earth minerals and so on, it still gets the best rating relative to the competitors. But
I'm not thinking of investing in mine.
yeah, you okay? Well, yeah, yeah. Well, you know, and I think that, by the way, I think part of the reason mining has this property of being so volatile is because it requires such long-range investments. I grew up in a mining town, and you know, when price of copper goes up, everybody goes to work, and when the price of copper goes down, they get laid off. But you know, it takes 5 years to start up, even to start up an existing mine takes years of preparation. So there's big lead lag effects. Yeah.
One question about the efficiency of investment. Long model, the long term, your model is very beautiful, but in the short term, we need to make the transition fast.
Yeah.
And what we see nowadays is a tendency to do a protectionist model of transition, where the states will say, okay, but the batteries needs to be produced in the states.
Yeah.
The European Union is going to replicate the policy.
Yeah.
So is this going to influence short term your course, because the rentability of the investment will flat somehow because it's not allocated in the most efficient way?
Well, yeah. So we're not arguing there might not be bottlenecks that would knock us off the path. I think one thing that, you know, that I reflected on in doing this is that we're very bad at thinking about exponential rates of change when they're large. So, you know, you can see just from this picture, you extrapolate this rollout, you hit the other curves up there in less than a decade. And so we're really at a critical point right now where, you know, solar energy is still just 1% or something of global power, but it's about to burst forward on the stage. And then the question is, how far can it go before it starts hitting roadblocks? And, you know, my guess is that, I mean, my guess is that this won't be it'll be a little bump, but it won't be a long-term change in the trend. You know, one of the reasons why I think renewables are going to have, one of the positive side effects are energy security, which with Ukraine we see is pretty important. It means if, you know, maybe that if you're in England, you have to pay more for your power than you do if you're in Arizona. But if you're willing to pay for it, you can get energy security regardless of the natural resources you have regarding as you do now. So I think that's going to be a big factor pushing countries toward it. And so we may even benefit from this isolationism in that regard, because it's yet another incentive to go renewable.
This is because in your graph, and I think that's, in your opinion, what is the role of the mitigation policies? Because in the nuclear power, you have the slope is different, and if you have the solar photovoltaics and another ones, it's because in the 80s, 90s, you have a different mitigation policies to promote specific kind of technologies. In your opinion, what is the role of the trade agreement and mitigation policies to change the slope of the different?
Yeah. Well, so one thing to realize is that renewables come in third when it comes to subsidies. So fossil fuels get the most subsidies, nuclear power gets the second, and then renewables, even adding them all up, come in third. And so, but subsidies are starting to be removed as these things become price competitive. Certainly, its policy, I think, is going to be really important for making these things happen. You have to have the political will to do this. I mean, when I was talking to my son, who I mentioned works at Federal Energy Regulation Commission, he said, problem, don't quote me on this, you know, those guys in Alabama could give a shit about renewable energy. And so they do everything they can to prevent the grid from being built out, to keep the good old boys, you know, in power. So it's that kind of place where the rubber hits the road. You know, Russia's going to fight against this, and you know, but when they start to have an internal fossil fuel economy and the rest of the world has a cheaper renewable economy, it becomes a bigger and bigger disadvantage for them. I'm not sure if I answered your question. Thank you. Good set of questions. I really enjoyed the discussion. Thank you.